Hello everyone. Today we will start the limit of a function. Before the definition of limit of a function, we will see the meaning of x tends to x0. Meaning of x tends to x0. Let x0 be a fixed real number and x be any real variable. These two quantities lie on the real line. Suppose this is a real line R and this x0 and x lying on this real line R. Only freedom to this x is to move along this real line R. The statement x tends to x0 means this x approaches to x0 or x tends to x0. The movement of x, this movement of this x can be done in two ways, that is from left or from right to x0. If x is to right, if this x is to right of this x0, it will approach to x0 from right, and we say that x tends to x0 from the right of this x0. It is indicated by x tends to x0 plus, means right hand limit, right hand. So similarly, when x is to left of x0, similarly, suppose this is real line R and here is suppose x and here is x0. Similarly, when this x is left to this x0, it will tends to x0 from left. This x tends to x0 from left, and it's shown by x tends to x0 minus. Now x tends to infinity is identically equal to x. Is identically equal to x increases without bound. Means you have this is the real line R and here is a point x, and suppose here is a 0 and minus infinity of the left hand of this x, and this x tends to minus infinity. And again this is real line R, and suppose here is infinity, and suppose here is 0 on this real line, and this is x. So x tends to infinity. That means x tends to minus infinity is decreases without bound. X tends to minus infinity decreases without bound, and x tends to infinity, x increases without bound, and x tends to minus infinity, x decreases without bound. This is the concept. Now we'll see the limit of function, concept of this limit of function. The concept of limit of function is linked with the nature of function on a deleted delta neighborhood. Deleted delta neighborhood. Deleted delta neighborhood. As delta gets close to 0 and the limit x tends to x0, limit x tends to x0 of a function f of x, is equal to L. Symbolize that L is a limit of f of x. This L is a limit of this f of x as this x tends to x0. That means this f of x tends to L as x tends to x0. It means that the value of this f of x get close to this L as desired by making x sufficiently close to x0. X sufficiently close to x0, and this statement is true even if f of x0 is not defined. Now we'll see the actual definition of limit of a function. Limit of a function. Let f be a real valued function. Let f be a real valued function defined for all x in the neighborhood of point x0 except possibly at x0 itself, and let L be the real number. Then this limit of a function f of x as x tends to x0 is equal to L. If for every epsilon is greater than 0, there exists a delta which is also greater than 0 such that 0 is strictly less than mod x minus x0 is strictly less than delta, and this implies that mod f of x minus L, which is strictly less than epsilon, or mod f of x minus L is strictly less than epsilon whenever 0 is less than mod x minus x0 is less than delta. Now see the remark. Geometrically, it means that if x is a deleted delta neighborhood of x0, the ordinate of height f of x lies between L minus epsilon and L plus epsilon. Now see the remark. In this definition, in this epsilon minus delta definition of limit of a function, the delta may depend on epsilon. This delta may depend on this epsilon, and x0, this delta may depends on epsilon and x0. In view of 0 is less than mod x minus x0, which is less than delta, the point x0 is excluded from the domain of f. Hence, the value of f at x0 is immaterial for the consideration of the limit of f of x, and thus f is necessarily not be defined at x is equal to x0. Even if f of x0 is defined, it may or may not happen that limit of a function f of x as x tends to x0 is equal to f of x0. And furthermore, epsilon minus delta definition does not help to find the limit of function, but it confirms whether the given number L is a limit. Now see the second remark. Let's see the second remark. In the problems involving epsilon minus delta technique, the main concern is to find delta is greater than 0 from a given epsilon is greater than 0. Make use of mod f of x minus L is less than epsilon. Make use of this and produce mod x minus x0 is strictly less than k into epsilon, constant into epsilon, where k is constant. Compare this with 0 is less than mod x minus x0 is less than delta. Compare this. Compare this with 0 is less than mod x minus x0 is less than delta to get delta is less than or is equal to k epsilon. This delta is less than or is equal to k epsilon. Here k is constant. Sometimes this does not work to get delta in terms of epsilon. In such cases, delta is less than or is equal to 1. Consider the deleted delta neighborhood. 0 is less than x minus x0. To get x0 minus delta is less than x is less than x0 plus delta. Then use mod f of x minus L is less than epsilon to produce mod f of x minus L is strictly less than h delta, where h is a constant, and this gives that this h delta is less than or is equal to epsilon. That is this delta is less than or is equal to epsilon upon h. Then define delta is equal to minimum of 1 epsilon by h, and therefore we produce or we solve some examples by using this. Now see the example. Prove that limit of a function f of x has x tends to 2 is equal to 7, where f of x is equal to 2x plus 3. 2x plus 3 and x belongs to the interval 0 to 5. Now see the solution of this problem. We will prove this. Limit of a function f of x as x tends to 2 is equal to 7. Now we have given that f of x is equal to 2x plus 3, and to prove limit of a function f of x as x tends to 2 is equal to 7. So let epsilon is greater than 0. This is also be given here. Let epsilon is greater than 0 be given here. Suppose epsilon is greater than 0 given, or consider epsilon is greater than 0. Okay. So mod f of x minus 7 is equal to f of x is 2x plus 3, so we can write here 2x plus 3 minus 7 as it is. So what we get? We get this is equal to mod 2x minus 4. This can be written as 2x minus 2. We choose delta is equal to epsilon by 2. Then for epsilon is greater than 0, there exists delta is greater than 0 such that 0 is less than mod x minus 2 is less than delta, and this implies that mod f of x minus 7 is strictly less than epsilon, and this confirms that confirms that 7 is the required limit. And therefore limit of a function f of x as x tends to 2 is equal to 7. Now we see the next problem. We'll see the another problem. Now we'll see another problem. Example 2. If f of x is equal to x square f of x is equal to x square if x is not is equal to 3, and f of x is equal to 4 if x is equal to 3 or at x is equal to 3. And then prove that prove that limit of a function f of x as x tends to 3 is equal to 9. We want to prove this. Solution. We show that for any epsilon is greater than 0, there is a delta which is greater than 0 such that 0 is less than mod x minus 3, which is less than delta, and this implies that mod f of x minus 9 is less than epsilon. Now we choose delta is less than or is equal to 1. We choose delta is less than or is equal to 1. Then 0 is less than mod x minus 3. 0 is less than mod x minus 3, which is less than 1. That is 3 minus 1 is less than x is less than 3 plus 1 is less than 3 plus 1. So what do you get? Or this can be written as 3 minus 1 is 2 is less than x is less than 3 plus 1 is 4. If x is not is equal to 3, and then mod f of x, this mod f of x minus 9 can be written as this is equal to mod f of x is x square, so here is x square minus 9, so we get this is equal to mod x minus 3 into mod x plus 3. So this is less than delta mod x plus 3 if mod x minus 3 is strictly less than delta, and therefore this is strictly less than delta mod x plus 3, and again this is strictly less than delta in bracket so x is now we take x is 4, so this is 4 plus 3 is less than if this is 2 is less than x is less than 4 and this x is not is equal to 3, and therefore this is strictly less than 7 delta is equal to epsilon. And if we choose delta is equal to minimum of 1 epsilon by 7, we have 0 is less than mod x minus 3 is less than delta, implies that mod f of x minus 9 is less than epsilon. We have this, and therefore this implies that limit of a function f of x as x tends to 3 is equal to 9. And now for second, for x is not is equal to 3, f of x is equal to x square. Then by first we get this. Limit of a function f of x as x tends to 3 is equal to 9, and here f of x is equal to 3, so f of 3 is equal to 4. f of 3 is equal to 4 from first is not is equal to limit of a function f of x as x tends to 3. Now you see the next example. Show that limit of a function 2x cube minus x square minus 8x plus 7 divided by x minus 1 as x tends to 1 is equal to minus 4. Now see the solution. Let we have the function f of x is equal to 2x cube minus x square minus 8x plus 7 divided by x minus 1. So that for any epsilon is greater than 0, there exists delta is greater than 0. so that for any epsilon is greater than 0, there exists delta is greater than 0, such that 0 is less than mod x minus 1 is less than delta, implies that mod f of x minus 4 is less than epsilon. This is a function f of x. This is a function f of x minus 4 is less than epsilon. And so, let delta is less than or is equal to epsilon. Let this delta is less than or 1. If delta is less than or is equal to 1, then 0 is less than mod x minus 1 is less than delta, and this implies that 0 is strictly less than mod x minus 1 is strictly less than 1, that is 0 is strictly less than x is strictly less than 2, and x is not is equal to 1, and x is not is equal to 1. Now what do you have? Now this function f of x can be written as 2x cube minus x square minus 8x plus 7. Factors of this polynomial is x minus 1 into 2x square plus x minus 7 divided by x minus 1, and this is equal to 2x square plus x minus 7 if x is not is equal to 1. If x is not is equal to 1, and therefore this implies that f of x minus 4 is equal to 2x square plus x minus 7 plus 4. This minus will be plus, and f of x is this 2x square plus x minus 7. This x1 minus 1, x minus 1 will be cancelled. We have 2x, f of x is equal to 2x square plus x minus 7. So, in place of f of x, we put this minus plus 4. So, this is equal to 2x square plus x minus 3, and factors of 2x square plus x minus 3 are x minus 1 and 2x plus 3. Again, this implies that mod f of x minus 4 can be written as mod x minus 1 mod 2x plus 3, and which is strictly less than delta mod 2x plus 3. If this mod x minus 1 is strictly less than delta, and therefore this implies that mod f of x minus 4 is strictly less than 2 into 2 plus 3 is equal to 2 into 2 4 plus 3 is 7. This is the delta here, delta into. So delta into 7 means 7 delta. If this 0 is less than x and x is less than 2 and this x is not equal to 1 again. If 7 delta is less than or equal to epsilon, if 7 delta is less than or equal to epsilon, then this delta is less than or equal to epsilon by 7. And thus delta is obtained in terms of epsilon. Choose delta is equal to minimum of 1 epsilon by 7. And then what you get? Then we get 0 is less than mod x minus 1 is less than delta. This implies that mod f of x minus 4 is strictly less than epsilon. Hence the required limit is minus 4. Hence the required limit is minus 4. And therefore we have proved here limit of a function 2x cube minus x square minus 8x plus 7 divided by x minus 1 as x tends to 1 is equal to minus 4. Now let's see the concept of right hand and left hand limits. Right hand limit and left hand limit. So right and left hand limits. Right hand left hand limits. In the process x tends to x0, the values of x may be greater or smaller than this x0. When x takes greater values than x0, when this x takes the greater values than x0, then x tends to x0 from the right and indicated by x tends to x0 plus or x tends to x0 plus x0 plus 0, and this leads to the right hand limit. Means right hand limit is limit of a function f of x as x tends to x0 plus is identically equal to f of x0 plus or f of x0 plus 0. Similarly, for left hand limit, when x takes smaller values than x0, when x takes smaller values than this x0, then x tends to this x0 from the left and is denoted by x tends to x0 minus or x tends to x0 minus 0. This defines the left hand limit of the function f of x. So, left hand limit is limit of a function f of x as x tends to x0 minus is identically is equal to f of x0 minus or f of x0 minus 0. Now, proper definitions of right hand limit and left hand limit we see. First, for right hand limit, f of x0 plus is identically equal to limit of a function f of x as x tends to x0 plus is equal to L if for any epsilon is greater than 0, there is a delta is greater than 0 such that x0 is less than x and this x is less than x0 plus delta, and this implies that mod f of x minus L is less than epsilon. This is the definition for right hand limit. Now we see the definition for left hand limit. F of x0 minus is identically is equal to limit of a function f of x as x tends to x0 minus is equal to L if for any epsilon is greater than 0, there exists delta is greater than 0 such that x0 minus delta is less than x and this x is less than x0. In the right hand limit, x0 is less than x and this x is less than x0 plus delta, and in the left hand limit, x0 minus delta is less than x and this x is less than x0, and this implies that mod f of x minus L is strictly less than epsilon. is strictly less than epsilon. Limit of a function f of x as x tends to x0 minus is equal to f of x0 minus, right here minus, is equal to limit of a function f of x0 minus h as h tends to 0, as h tends to 0, and limit of a function f of x as x tends to x0 plus is equal to f of x0 plus is equal to limit of a function f of x0 plus h as h tends to 0, as h tends to 0. Now, the limit of a function f of x exists at x0 if both the limits f of x0 plus and f of x0 minus exist, and these are equal. Then limits, right hand limit and left hand limit will be exist. If either or both of these limits do not exist, the limit of a function f of x at x0 does not exist. And if both the limits exist but are unequal, then the limit of a function f of x at x0 does not exist. I will see some examples. Let f of x is equal to 2x minus 1 and x is less than 0, and f of x is equal to 2 at x is equal to 0, and f of x is equal to 2x plus 1 and at x is greater than 0. And to find out limit of a function f of x, as x tends to 0 plus limit of a function f of x at x tends to 0 minus left hand, this is right hand limit, this is left hand, find right hand limit, left hand limit, and the limit of a function f of x at x tends to 0. We want to find this. Now see the solution of this problem. Limit of a function f of x as x tends to 0 minus, that is left hand limit, f of x is equal to limit of a function f of 0 plus h as h tends to 0, this can be written as limit as h tends to 0 in bracket. Here is 2x minus 1, so 2x is 0, 0 plus x is 0 plus h, f of x is 0 plus h plus 1, and this is equal to limit as h tends to 0 of a function 2h plus 1 is equal to h is 0, so this will be 0 and this will be 1. So this is for right hand limit. This is for right hand limit. Right hand limit is equal to limit of function f of 0 plus h as h tends to 0, as h tends to 0, and this is equal to limit of a function h tends to 0 of a function 0 plus h, because this is a f of x is 0 plus h, so in place of this x here is 0 plus h plus 1 is equal to limit h tends to 0 to h plus 1 is equal to 1. So what do we have? Now limit of a function f of x as x tends to 0 minus, that is left hand limit, is equal to limit of a function f 0 minus h for left hand limit as h tends to 0. So what do you get? You get this is equal to limit as h tends to 0, here 2 0 minus h, this is f of x, where x is 0 minus h, so in place of x we have 0 minus h minus 0 minus h minus 1 is equal to limit as h tends to 0 is minus 2h minus 1 is equal to, this will be 0 and we have minus 1. And therefore since f of 0 plus is not is equal to f of 0 minus, means right hand limit is not is equal to left hand limit, because value of right hand limit is equal to 1 and value of left hand limit is minus 1. So limit of a function f of x as x tends to 0 does not exist. Does not exist. It does not exist. So we prove this, or we solve this problem also. Now see we have so many examples here. So you can calculate all these examples. Tomorrow remaining examples we will take tomorrow. Today we will stop here. Now these video lectures I will upload on YouTube, which link is provided to you of this YouTube link. I will already provide it to you. You click on this link and subscribe and you will get the regular notifications of the video lectures. Tomorrow we will see these types examples again, and then other article, next article is next article will be the theorems on this limit. We will discuss tomorrow. Okay, thank you.